where I spend half my time nowadays, doing a lot of work with property-based testing in practice. So QuickCheck itself is a tool that Koen Klassen and I came up with more than 10 years ago, and those of you who know Haskell probably know of it. Cubic has created another version of the tool in Erlang, and that's the one that the company's activities are based on, that I'm going to tell you about today. So, first of all, a very quick demo, just to be on the same page. What is QuickCheck? Here is some Erlang code that declares two properties of the reverse function. I showed you the same properties in Haskell in my first lecture. So you can see that the properties are just expressed as Erlang function definitions, but we have explicit for alls, and so they look like logical statements. So if I take these properties and start the Erlang shell, then I can compile that code and then invoke the Erlang version of QuickCheck on, what was my file called? Rev. The property that says reverse x's is x's, and that succeeds. Or indeed on the wrong property. And that generates a random test case that fails, this -4, 2. Oh dear, why is that? Yeah, I guess I probably can. That's better. Okay, so first of all you see a randomly generated case, and then it shrinks and we end up with the minimal failing test case. So this is what QuickCheck does. We start off with properties. We generate a lot of test cases from them, and we run the tests until one fails, at which point we take that test case and we search for a smaller test case that also fails. And we end up with some kind of minimal example. And this shrinking process is really incredibly valuable for testing. So when we generate random tests for real software, then they're often very large, and they're very random. Obviously. Random tests contain a whole lot of noise that has nothing to do with an actual test failure. So when a test fails, you've got all kinds of irrelevant nonsense in there, plus one or two features of the test case that make the test fail. And if you try and diagnose the problem from a large random test case, then you'll be spending more time than you perhaps might have spent testing in some other manner. So that's the purpose of shrinking. It's to extract the signal from the noise, so to say, and present the user with a counterexample that is concise and easy to diagnose. We saw it for the reverse function. I'm going to show you for some more interesting cases in a little while. So, if we compare testing with generated tests from properties to conventional testing, then it's great. You don't have to write as much test code, because you can write one property instead of many test cases. You'll get better testing, because you'll be able to generate lots of combinations that you'd never think of testing by hand. And you have to spend less time diagnosing failures, because they get minimized to these smallest failing examples. It's all great, right? Well, what more is there to say? More than you might think, actually. So a couple of years ago, we ran an experiment with a group of students. Unfortunately, only about this many. The more the better for getting statistically significant results. But we divided them into two groups, and we asked each group to solve some programming problems, asking one group to write unit tests for their code, that is, to write single test cases, and asking the other group to write QuickCheck properties. So we asked all students to write test code for their solutions, but they were to use two different techniques. So one of the problems that we gave them had an API of 4 or 5 functions, which was very well specified in the problem description. So that we were able to take one student's test suite and use it to test another student's code. And that let us evaluate how good the test suites were that were developed in the two different styles. And the results that we found surprised us rather. Here you see the quality of the test suite in terms of how many of the other student solutions could it reject, demonstrate there were bugs in. So down here, this is a test suite that could find bugs in 11 of the student solutions, and there were only 11 buggy ones. So this test suite could find all possible bugs. Down here, there are test suites that could find no bugs at all. And if you look at the colors on these things, you can see that the students that we asked to write unit tests, conventional test cases, by and large, they developed test suites that could find a fair number of bugs, but not all. The students that we asked to write quick check tests over here did a lot better. One of them could find every possible bug, and the other two here, if you look at this, the worst quick check properties were as effective at finding bugs as the best set of test cases. That's a good result. And it's actually statistically significant, even with a small number of students. But what's this? These are test suites that could find no bugs whatsoever, and almost all of them were produced by students who were to write quick check properties. How could they fail so badly? How can you write a test suite that can find no bugs at all? Write no tests. Exactly. And that's what these students did. So what we can learn from this is that if you write quick check properties, they'll be very effective at finding errors. Yes?
I'm wondering if this could have been affected by the requirements for the task, if it was sort of phrased in a property kind of manner rather than a sort of operational manner that may have led to sort of better thinking along the lines that would be productive?
We tried to give them problems of several different sorts.
Okay.
So I hope that there's not much surprise. But this experiment is too small scale, so maybe it wasn't. Nevertheless, it's interesting. It's interesting that if you write the properties, they work very well. But evidently, writing properties is harder than writing single test cases. And that was a result that surprised me. But it's essentially the same as saying that it's easier to come up with examples than it is to come up with a formal specification. And you know, we see that clearly in the result of this experiment. So let's look a bit more closely at what happens when you start writing properties for real code. This is part of a real test suite. It's for the base 64 encoding that comes as part of the Erlang distribution. Who remembers base 64 encoding? Good Lord. Okay, so what it does is it takes binary data and it breaks it into 6-bit chunks and then encodes each chunk as some kind of printable character. And it's used for taking email attachments and encoding them, because email, you know, SMTP is a text-based protocol. So you need to encode the attachments so that they don't confuse the protocol by containing valid protocol commands. Base64 encoding does that. So here you can see I've got one test that encodes this string and then checks that the result is equal to this. It's a binary string actually, but you can see the characters that the base64 encoding produces. So there's one test case, there's another, a third, and a fourth. And those are the tests that are run when the Erlang distribution is built. Okay, so look at the form of these things. We call a function under test on a fixed input, and we compare the answer against an expected result. This is the form of the vast majority of test cases in industry. There's just lots and lots and lots of things that look like this. So let's write a property. We're going to be able to do a lot better. Let us, first of all, generate all, or we'll quantify. We'll say for all data that is a list of bytes, then we'll call base64 encoding on data. That's much better than those 4 sample strings in the fixed set of tests. So let me take an arbitrary list of bytes and call the encoder on it. I'll get, oh, what do I put instead of those question marks? So this is a moment at which many people who try to use property-based testing get stuck. They can't think what to put there. Well, they could write another base64 encoder perhaps, but what's the point of that? Why write your code twice? For a start, it's twice as much work. And secondly, if you're going to make a mistake, you'll probably make the same one in each case. So you wouldn't even get good testing. So at this point, many people get stuck. But if we go back to the tests, we can ask ourselves, where did these expected results come from? Okay, in order to write this test case, you have to come up with those. So here's 3 possibilities. First one, someone applied the base64 encoding algorithm by hand to those strings and figured out what the encoding should be. Who believes that's what happened? Okay, I think you're probably right. So, of course, somebody could have done that, but much more likely is that the developer had another base64 encoder at hand and just ran the test cases through that encoder, copied and pasted the output into his own test suite. Actually, there's a third possibility, that they were produced by the same base64 encoder. In other words, the developer wrote the encoder first, ran it on some test inputs, and copied and pasted the result into his own test suite. It's not as silly as it sounds, because it at least gives you tests that you can run that will detect a change in your encoder. So if you're optimizing the encoder later on, for example, there's a chance that you will catch those errors. But it's not terribly effective. Now, at this point,
It's also easier. That is correct, rather than produce the results.
Yeah, sure. At this point, I usually like to ask people, moment of shame, who has done this? Okay, well, many of you have not. That's rather surprising. Actually, when I ask that question, I give this part of this talk to industrial developers as well, and usually every hand in the room goes up. Okay, so let's think about these possibilities then, because each possibility, or 2 of the possibilities, can give us ideas for writing properties. If the developer has another base64 encoder, why not write a property that runs that encoder too, and just compares the results? So you might wonder, if you've got another one, why are you writing a new one? But it might be that you want one in Erlang for the Erlang libraries, and you have one in C, for example. Or it might be that you have one that you want to own the copyright to, and you have one that's covered by a license that won't let you use it the way you want to. So, at any rate, the various reasons why you might not want to use the other encoder in production, they don't apply to your tests. So you can make use of that idea to write a property for testing, at least. Even in this case, if the developer is cheating and using the same base64 encoder, well, you can use that idea to write a property by, for example, keeping a fixed old version and testing new versions against that. And that is a useful technique, actually. If you first of all write a simple encoder and then start optimizing it, you can use the simple encoder to test the optimized one. If what happened was that the developer converted the data by hand, then all bets are off. We can't take advantage of that. Just let that person continue testing by hand. Something else we can do, of course, which I'm sure you all thought of, first thing that occurred to me, was write what we call a round-trip property. So if you're writing a base64 encoder, you're almost certainly writing a decoder as well. So what's more tempting than to write a property that says, for any list, if you encode it and then decode it again, you get the same result back. In this case, decoding returns a binary type, so there's a type conversion in there, but ignore it. It's basically saying encode followed by decode is the identity. And this is a very effective property to test. It can find lots of bugs that you might write in your encoders. But it's worth thinking about, what is it testing exactly? It's not testing that you've implemented base 64 encoding, because you could take any encoding whatsoever that has a corresponding decoder, and this property would pass. So if you've consistently misunderstood what base 64 encoding is, then this property will not reveal that. On the other hand, if you simply make a mistake in implementing one side, the encoder or the decoder, then the property is very effective at discovering that. And in this case, actually, the implementations are both table-driven. So there are two tables in there, an encoding table and a decoding table. They're very big, and it would be very easy to make a mistake in one of them. And most such mistakes would not be revealed by the 4-test test suite, but they are guaranteed to be revealed by this property, given enough testing time. So a useful lesson from this is that although this isn't a complete specification at all of base 64, it's a very useful test property, and it can find a lot of bugs. And in practice, a good way to test this code might well be to write this property and then reuse the unit tests that I already showed you, because those do test that in those two cases at least, it's really base 64 encoding that we're doing.
The property will guarantee that the bugs will be found.
Yes.
And my question is, if you have some statistics of bugs that weren't found by the quick check and were found later in production.
So when I say guarantee, what I mean is that if you keep running tests arbitrarily long, then you will find an error with probability 1. Sometimes it might take the life of the universe.
But it doesn't guarantee that it's free of errors. So.
No, it doesn't guarantee it's free of errors, but it will guarantee that this property holds. Because eventually, random testing will produce every possible input.
But do you have evidence of bugs being found? Do the testing that it found no bugs, and then in production,
yes. So that in more complex situations that sometimes happens because. Well, it depends actually on how carefully you control the distribution of test cases. So with random testing, the distribution of tests is vitally important. And if you choose a good distribution, then I'm not sure we've actually seen bugs slipping through. But I'm going to talk more about bugs we found than bugs we missed. Okay, so very tiny examples. I want to show you how we test C code as well. Oh darn, there we are, it's our bot. So I am actually able to write C, although I'm not very good at it. Here is some C code. I hope you can read it. It implements a queue as a circular buffer. So here's the type definition. A queue contains a pointer to the buffer where we're going to put data, and the index where we're going to put data in, where we're going to take it out, and the size. So here's the code for creating a new queue. We have to allocate a buffer of the right size, initialize that struct up there, allocate some space to hold that, initialize that space, and return the pointer. Here's how we put something into a queue. We write it to the buffer at the input pointer, and we increment the input pointer modulo the size. Very simple. Here's how we take stuff out. We read from the buffer at the output pointer, and we increment the output pointer modulo the size. And here's how we find out how many elements are in the queue at the moment. We take the difference between the input and the output, modulo the size. Okay, so very simple data structure implementation, obviously correct. Let me just switch back to my Erlang shell. We can test it because we've made a tool for use in Erlang that can take C code and it compiles it and it makes it directly callable from Erlang. So that I can now create a queue of size 10, for example, and I get back a representation in Erlang of the C value. So I've got a pointer to a struct and at that address. And then I can put a 1 into it, and put a 2 into it, do a get, whoops. Let's pass it to pointer, of course. Do another get, do another get. There we are. I've got memory with zeros in it. Oh, there's the 1 and 2 again, and so on. Remember, it's a circular buffer. And if I want to, I can also dereference the pointer. And I get back an Erlang structure that shows me that the input pointer is 2, the output pointer is 3, the size is 10. There's the pointer to integers in the memory. And I can dereference other things as well, like a pointer to a character at address 0, for example. Oh, segmentation fault. So that's nice. We can crash the C code. It doesn't crash the Erlang, of course. If it did, we wouldn't be able to use quick check to analyze that kind of crash in C code. So the point of this is that I can now test C code by calling it from Erlang. And let me talk about how we do that. Unlike the simple functions that I showed you tests for before, the C code has side effects. It has internal state. And we have to model that in an Erlang specification. Otherwise, we're not going to be able to run sensible tests. So we have an approach that we always use for testing stateful code. We generate test cases that are a sequence of API calls. We define a functional model of the state, and we define state transitions for each API call. And then we just check postconditions. So we check that the actual result from calling the C corresponds to the model state. So in this case, a test case might put 1, put 2, get a value, put 3, do another get. And we can model the state just by the list of values that should be in the queue, that we expect to be in the queue. That's a very simple functional model. And then the postconditions will just check that every time we do a get, the result that C returns is the first element in the queue. Here are some code fragments. We write state transition functions in Erlang. This one, and maybe you can't read Erlang, but it's pattern matching on a call in the test case. So it's saying when we do a put of the value x, then the effect on the model, the state model, is to append x to the list of elements in the queue. When we do a get, the effect in the model is to take the tail of that list of elements. The postconditions also say the postcondition for get is that the actual result is the head of the list. And for size, it's that the actual result is the length of the list. So I hope you can see that this is very, very simple functional code. And then the properties that we test are very much the same when we test stateful code. We write some quick check generators that can generate test cases of this sort. And the property says, for all command sequences generated using these functions, when we run the commands, the result is OK. And the result is OK if all the postconditions held. So let's see what happens when I test my code. OK. I'll need to compile my specification. And I can test the property. Darn, it failed. It failed in the test case strength. There's a lot of output. First of all, we see output from the initial random test, which is very long. You don't want to read that. And then we see the output from the actual shrunk test. And down at the bottom, we can see a kind of pretty printed version that shows you what's happening. So what do? Well, we created a queue of size 1. We put 0 into it. We put 1 into it. And we called get. OK, we put in 0 and 1 into a queue. We called get. What should we get? 0. 0, obviously. But we got 1. Why is that? What went wrong?
When
Get did advance the pointer. Yeah.
Because you only have the size.
Just implemented the stack.
Actually, I didn't.
You wrote it in C.
Yeah. How big is the queue?
1.
1. How many elements did I put in?
2.
So what happened? The 1 overwrote the 0. And the result. Okay. Whose fault is that? Okay, obviously mine, somehow, but is it the fault of the C code, or is it the fault of the test? So, you might discuss whether the C code should do something more sensible than simply overwrite data if you call too many puts. But I'm imagining that this is simple C code, and you know the test should respect its preconditions. And this test does not. So the problem here is that the specification is wrong. The specification should say there's a precondition that before you do a put, there must be space for it. So let me go to my code. Here is the specification, and there are some preconditions in here. Okay, so once again, this is an Erlang function that matches on the call and then returns the precondition. Here's a precondition for get. It says that there must be something in the queue. And, oh look, somebody commented out a precondition here. This is the precondition for put, which says that the length of the elements in the queue must be less than the size of the queue. That sounds good, doesn't it? Let me put that precondition back in. Okay, and now if I recompile my spec, then I can actually rerun that test. Oh no, I won't do that. I'll test again, and this should no longer happen. There we are. 100 tests passed, it must be right. You don't believe me? Let's run another 100. Okay, so things are looking good. Actually, up here, I have a specification of which tests to generate. So this says we start off in an initial state, we move to the created state by calling new, and then in the created state we can call put or we can call get. So now I can be pretty confident that put and get work. But I commented out the line that says, and we can call size. We often do that because I like to test a part of the API first and make sure I'm confident in it, and then gradually add more functions to the tests. So let's test size also. Recompile the spec, retest. Oh, something else failed. Okay, what happened here? I created a queue of size 1. I put a 0 into it. That's okay. I asked for the size. It returned 0. Okay, which is at fault, the C code or the test? The C code, surely. This cannot be right. So let's look at the C code again. Here's the size function. Okay, the queue is of size 1. I've put something into it. How can this function possibly return 0? That's right. So the buffer is of size 1. As soon as I put something into it, I incremented the input pointer, and it immediately wrapped around. I took it modulo 1, for goodness sake. That's always 0. So this is a classic problem with circular buffers, that with the obvious representation, you can't distinguish between a full and an empty one. What should I do? I have to fix the C code. I could add a Boolean, but here's a sweet hack. When I'm asked to create something of size n, let's just make it size n plus 1. So if I do that, then a good test will never fill it. It's going to work, right? Okay, so now I have to, of course, recompile the C code, restart it, since that was where the bug was, and I can repeat the test. I will actually this time check that very same test. So if I take my property and I test it on the current counterexample, yes, the test now passes. Okay, So just, I mean, we might as well run a few more tests, eh? What? It failed again. So what happened this time? We created a queue of size 1, that's really 2. We put a 0 into it, that's all right. I did a get, that returns 0, that's also all right. So now the queue is empty. I put a 0 into it again, that's all right. And I asked for the size, and the C said, -1? Well, that's clearly wrong. How could that possibly happen? Look, I'm taking the difference of the input and output pointer modulo 2. There's a modulo in there. That can never give a negative result. Really? But if I take -1 rem2 in Erlang, oh dear. Yeah, so what's happened here is I put two things in. The input pointer has wrapped around. I incremented the output pointer by taking one thing out. So, 0 minus 1, it's -1. Okay, what shall I do? How shall I fix this? Yeah. Sometimes people suggest taking the absolute value. That's quite cool, actually, because, of course, you then get a slightly more complex failing case. But this is the right thing to do. So let's recompile. And rerun that test. That now works. And rerun lots of tests. Look. 300 tests say it works now. And indeed, I believe that it does. Okay. So, how am I doing? All right? So, what have we seen from that? Well, we've seen that one property was able to find many bugs. That's very good for finding a lot of bugs with little work. But also, I hope you've seen now that the shrinking process that generated those minimal examples made the bugs really very easy to find. That was a tiny example. Can we do it for real? Well, yes, we are at the moment. So back home in Gothenburg, as I speak, well, maybe not just as I speak, because most people are on holiday, but people are developing quick-check specifications of this kind for the system software that runs on the processors in cars. Cars have about 50 to 100 processors in them nowadays, and the basic software that runs on them is standardized. It's supposed to meet the so-called AUTOSAR spec. And the purpose of this specification is to enable car manufacturers to buy software from whichever vendor they like. There are many vendors for this system software. If you buy a particular component for your car, it may come with some system software on it. And of course, since they all fulfill the standard, they should all work together. What do you know? Sometimes they don't. In fact, usually they don't. So the software looks something like this. This is a diagram of the architecture. There are a number of protocol stacks. There are some communication services. There's a diagnostic cluster. In total, I haven't got everything in this picture, but there's about 50 modules in the standard. And Volvo, they want to be able to do things like buy this software from one supplier and say, oh no, the CAN bus stack sucks. Let's take that out and put in somebody else's. If it's all standards compliant, it should all work. So they really, really want to make sure that this stuff does correspond to the standard. And yes?
Each of the boxes or each of the stacks, or?
The standards, oh, that's an interesting point. The standards specify each of the boxes, but the vendors implement each of the stacks. So they don't necessarily implement some of the interfaces that the standard specifies. Nevertheless, their stack should behave as though they implement each box separately.
So what matters is the top interface of the tops of the stacks.
Yes, well, they can actually divide up modules inside in different ways, but at the points where they have clustered them, then it must follow the standard, the implications of the standard. So, Volvo's plan is when they buy software, insist that it's certified. It will be certified by SP, the Swedish certification agency. So you might wonder, how can SP possibly certify that the software meets the standard? Well, they will run a whole lot of quick check tests, which are being developed at Cubic at the moment. So what we're doing is we're using state machines, like the one that I just used to test that C code, to generate API calls to these components, or to combinations of them. And then we also mock the other components that might be called. So if we make an API call to a protocol layer, for example, we expect it to make certain API calls to the lower layers. So we need to detect those calls, which we do by creating mocks. So the property that we check is that the post conditions hold for all of the API calls that we make, and the correct calls are made to other modules. Here's one of the bugs we found. So this is a bug in a CAN bus protocol. The CAN bus is a very common bus in vehicles. And every application that talks on the CAN bus has an identifier. It's CAN ID. That identifier is also its priority for the bus. So if you have identifier 100 and somebody else has priority 200, and you both want to send a message, you go first. So that's very important, because you might have safety critical messages on the bus at the same time as the stereo is streaming music to the back speakers or something. So in the old days, the standard CAN ID was 11 bits. But nowadays, allowing 2,000 components to talk on the bus just isn't enough in a modern car. And so there's a new version of the protocol that also allows an extended CAN ID of 29 bits. But even though the ID can be in two different forms, it's the value that matters for bus priority. So here is a test case that failed. It's in the red box.